which we have discussed Monte Carlo simulation, right. So, to quickly rephrase what we discussed, or recap rather I should say. So, we discussed about Monte Carlo simulation, or rather I should say MCS, and in MCS the idea is that the probability of failure you are trying to calculate is actually an expectation, and that expectation can be calculated by using sampling. In one sentence, if I have to say, that is the whole idea of Monte Carlo simulation. So, if you remember what we did was, we said that P f is equal to integration indicator function g of x less than 0 f x x dx, and you will do it over the total domain minus infinite to plus infinite basically, right. That is what we did, and then we said that this is nothing but equal to expectation with respect to the PDF of x. Okay. So, PDF of x, I generally write x, but I am going to change the notation today. You will realize later why am I doing it. So, I will write it with respect to the PDF of x of the indicator function g x less than 0, right.
So, we were doing this for the failure domain, the integration or the full domain?
You tell me.
Okay, after the indicator domain, it will give 0 if the g.
So, that is the function of the indicator function. If we are doing over the failure domain, we do not need the indicator function, because we are doing over the whole domain, because without doing over the whole domain I cannot write expectation, and that is why I am writing it in this form, and that is why the expectation term is coming up here, right. So, and from here we are now saying that, or we said yesterday that P f hat is equal to 1 by n summation I equal to 1 to n indicator function g of x I less than 0, where your x I is sample from f x of x, right, where your x I is sample from the PDF of x. It cannot be just any arbitrary sample, it has to follow the distribution, because if it is not following the distribution, the expectation that will not hold. So, that is why it is important that you are, when you are sampling, you sample from the distribution of the, right. And with that we discussed yesterday also, right, that the algorithm will look like. The algo is very simple. Your input will be f x x and n, and then you will start a counter equal to 0, and by the way this is equal to, we discussed it also, number of failure points by number of, because if the indicator function it will give the number of failure point, right, counter equal to 0, and then for I equal to 1 to n, you will calculate y I, which is equal to g of x I, and you will then have a if condition. If y I less than 0, you will update your counter plus 1, and right, and finally your probability of failure is n, or rather in this case it is counter divided by n. This is what we discussed yesterday, right. We discussed one more thing, which was about the convergence rate, and we saw that the convergence rate is proportional to 1 by root n. And remember the that 1 by root n, that comes from the fact that convergence is decided in terms of variance or coefficient of variation. Even if I do in terms of variance, you will still end up with 1 by root n. Okay. But one thing that we did not discuss, so let us complete that part before we move to anything new. So, now this equation, right, P f hat, will you agree with me if I say this equation P f hat, or rather this P f hat is an estimator of P f? If I use this terminology that P f hat is an estimator of P f, will you agree? To agree, you have to first know what is an estimator, right? So, it is estimating P f, you are approximating P f by P f hat, so it is an estimator, right? It is an estimator because it is not the exact value. If it was exact, then I will say P f hat is equal to P f. But since P f hat will never be equal to P f, except in the case you have infinite number of samples, which you will never have. So, that means for a finite n, we can say that P f hat is an estimator of P f, right. So, if P f hat is an estimator of P f, the question naturally comes, is it an unbiased estimator? Is P f hat an unbiased estimator? Can someone tell me what do you understand, or can someone define what is an unbiased estimator? When will we say that an unbiased estimator, or rather when will we say that an estimator is unbiased? I mean, it will never follow, right? I mean, there is no distribution, it is a value. Think about it. We are not, what are you computing here? P f hat. P f hat, right?
So it doesn't depend on the P f depends upon n. So if n is like close to infinity, then the value it will give will be different from n when n is small. So it will be biased on value n.
No, it is biased or unbiased, we will come to that. I am asking, what do you mean by unbiased estimator? Can you define what is an unbiased estimator? It doesn't
depend on the distribution.
It definitely depends on distribution.
Well, what kind of distribution?
The fx, if you change fx, it will not match.
It is
So, like if we change the number n, it should not change the P f hat.
It will change.
Very much.
It will change.
Always.
I mean, it will always change. That is that has nothing to do with unbiased or biased. That is convergence we are talking about. When do you say something is unbiased?
doesn't depend, its outcome doesn't depend on any other.
Yes, but in this case that does not hold. So, you have to be more specific.
The random variables.
That is the definition of unbiased. If something is unbiased, think about linear regression. Why do you call that B term bias? Because if you take expectation that and everything is 0, that B will come out. So, unbiased estimator means if you take expectation of this P f hat, then that should match theoretically with the thing you are trying to estimate. If it matches, then that is an unbiased estimator. Expectation of P f hat should be equal to P f. Okay. If expectation of P f hat is not equal to P f, then that is a biased estimator. For example, given a sample, how do you compute standard deviation? Can you tell me? You have samples of x. How do you compute standard deviation? The formula? Yeah, that is in summation you will, right? You have finite number of samples. So, in terms of summation you tell me. Summation, how do you compute standard deviation?
The sample minus the mean
Square?
multiplied the function.
What function? Divided by? n or n minus 1?
N minus 1.
Why n minus 1? Why not n?
Because we are
And
knowing
mean will be 0.
Because if you divide by n, that's a biased estimator. If you divide by n minus 1, that's an unbiased estimator. So when you calculate standard deviation by 1 minus n, for mean you don't do 1 minus n, you do 1 by n, right? But for sample standard deviation, you do 1 by n minus 1 summation xi minus mu whole square, right? Why this n minus 1? Why not n? Because common sense is saying it should be n, right? If you do n minus 1, then only it will match with that. If you take expectation of that variance 1 by n minus 1 summation, that will give you the actual variance. But if you take 1 by n, you will get sigma square by n. So it is biased by a factor of 1 by n. So unbiased estimator is when expectation of your estimator is equal to the true quantity. When and from where it is coming? From your definition, if I say you are calculating PF, right? You can calculate PF n number of times. 10,000 samples, right? Sample 10,000, find out PF. Again sample 10,000, find out PF hat. Again sample 10,000, find out PF hat. And this you can repeat infinite number of times, right? Expectation means that this PF hat you have calculated, if you take expectation of that, that should not be biased, that should match with PF. So that is the idea of unbiased estimator. So an estimator is said to be unbiased if and only if expectation of the estimator is equal to the true quantity. Clear? Any question?
1 by n minus 1 can be called 1 by n minus 1.
Try taking expectation of that quantity and see if you can get the variance or not. Try taking expectation of 1 by n minus 1 and 1 by n and see if you can get the variance or not. Exact variance, not sigma hat, sigma square, not sigma hat square, I mean. Okay. So, coming back. An estimator is unbiased if expectation of the estimator is equal to the quantity we are trying to estimate. We are trying to estimate. Okay. That is when you will call it an unbiased estimator. So that means that basically means if I take expectation of this second equation and if that gives me PF, then that will be an, I will call it as an unbiased estimator. So let us see. Expectation of PF hat. First question should be expectation with respect to what? Expectation with respect to f. So f of x I am writing f. Okay. This is equal to, what is the estimator? 1 by n summation indicator function, right. So 1 by n, expectation of summation is equal to summation of expectation, expectation goes inside, summation expectation of your indicator function, and then inside you have gx less than 0, right. Your indicator function, and then inside you have g of xi in this case less than 0, and then I will goes from 1 to n, right. Okay. Okay. So now there are two ways of deriving it. Let us go by the first way, which is the easiest way, assuming you understand distribution. Indicator function of g of xi less than 0. What distribution is it following? Indicator function of g of xi less than 0. What do you think this what distribution is it following? What? Yeah, Asif. What distribution? Bernoulli or binomial? How many things binomial? And how many things Bernoulli? What is the difference between Bernoulli and binomial? You raise hand for Bernoulli, right?
Bernoulli is the specific case of binomial.
We only care about number of success and failure
In binomial. In this case, it is xi, so it's the ith trial. What will it be? Ith trial. One trial. The output of I is what? 0 or 1. So it's like throwing the toss, the coin, or throwing the dice. In this case, coin I will say is a better example. Ith time, and what will happen? Only the ith time, not I minus 1, not I minus 2. It's a Bernoulli distribution, right? So if it is Bernoulli distribution, what is the mean? P. What is P in this case? Probability of failure, right? So then what will you get? Expectation will be equal to what? P of f. It is a Bernoulli distribution, right? That much you agree. Everyone understand it's a Bernoulli distribution and not a binomial distribution, because it's a one trial we are talking about, right? What is the chance that it will be equal to 1? When will it be equal to 1? When it fails. And when will it be equal to 0? When it is safe. What is the chance it will be equal to 1? P of f, probability of failure. So that expectation will be equal to what? P of f. Then 1 by n summation of P of f, what will you get? 1 by n multiplied by n P f. N and n will cancel out. P f. Summation of a constant is equal to n times constant. This is equal to 1 or 0, right? Which means this is a Bernoulli distribution. Okay, and it is one with probability P of f, right? So therefore, expectation f of P f hat is equal to 1 by n summation P f, which is equal to P f, which means it is a unbiased estimator.
Sir, let's add on P or F, so first line.
Wherever you want to put it. Be consistent, I am not consistent, should be P hat. Yeah, you are right. I mean it's your notation, right? You just be consistent, that's okay. It's an estimate, obviously. I mean, if I follow the textbook, it should be what P, because P is the probability and that is what you are estimating. So in that sense, it's not the failure event is not changing. So in that sense, but it's okay. Okay. Any doubt? What is the other way of deriving it? Write the expression of expectation. What is expectation equal to? Expectation, what is the formula for expectation? Not summation, integration. Summation is an approximation. I, there will be an integration, right, of the quantity inside. Because it is integration, I can remove the I, but yeah, that's because it will not change with I. F x x dx, right? What is this quantity? Is it not P f? You get back at the same thing. Okay. So this is a unbiased estimator. Okay. Keep in mind, by the way, in many cases we use biased estimator also. So, when I am saying unbiased, do not think that okay, I cannot use an estimator if it is not unbiased. It is not like that. In many applications we use biased estimator, but it is a good mathematical exercise to know if your estimator is biased or unbiased. You should know, but it is not like you should not use the bias estimator. In this case, the benefit is there is a theoretical proof that if you repeat it infinite number of times the experiments, you will get exact PF. That is the benefit. If it is biased, then you repeat the experiments infinite number of times. Remember, this is one experiment is finding out PF. So, find out PF infinite number of times, still you will not get PF. You will get it divided by some factor, right. So, that is the whole thing. So, mathematically rigorous all, but then we are engineers. I do not think there is anyone from science here. So, if everyone is an engineer, at the end of the day you have to design something, and at every step you will do approximations, you will use whatever is available, you will always have a tolerance and that you can account for. Okay. Okay. So, let us quickly solve the problem that I mentioned yesterday to understand the number of sample requirement, right. What was the number of formula that we derived yesterday? COV is equal to square root of PF or 1 minus PF, I think 1 minus PF by NPF. This was what we derived yesterday, right. And I said let us say I want COV is equal to point. So, I want to estimate let us say PF is in the order of 10 to the power minus 4, okay, and I want 5% confidence. So, this is equal to 5%, which means 0.05 is equal to 1 minus 0.1231, right, divided by n 0.0001, right, which means n is equal to, or rather n is equal to, I will take a square. So, 1 minus 0.0001 divided by 0.05 whole square multiplied by 0.0001, right. So, in the numerator you will have what 0.9999 divided by, this will give you what 0.0025 multiplied by 0.0001. So, if I remove the decimal, it will, I can multiply it by 1000. So, I can remove it and remove this thing, right, and this is also there. So, if I remove it by 2, 3, 4, right. So, I will add 4 zeros. So, now divide it and see what you are getting. Okay. So, clearly for this let us take 99 as plus 1 just for approximation. So, this will give you what 4, 40, 400, 4000, 40,000, 400,000, 4 million. So, approximately 4 million samples is what you will need for estimating it with 5% confidence. If it is 1%, you can imagine what will happen. So, this is approximately equal to 4 million, right. So, we already know that the convergence rate is slow 1 by root of over n, but this is an example which shows everything, which put everything into perspective. You can imagine that 4 million simulation for just 10 to the power minus 4. Now, do you think 10 to the power minus 4 is a low probability, high probability, okay probability? What do you think it is? Low. For our engineering system, 10 to the power minus 4 is okay kind of probability. I will call it a rare event. That means little bit low probability if it is in the range of 10 to the power minus 5 to 10 to the power minus 8. Very rare event 10 to the power minus 8 to 10 to the power minus 12. Extremely rare event 10 to the power minus 12 to 10 to the power minus 20. So, when you design a nuclear reactor, for example, you target 10 to the power minus 15 or something like that. Nuclear reactor, the size you can imagine 10 to the power minus 15 you can imagine doing MCS. I think you have to take birth 5, 6, 7 times, and then still that calculation will go on. Okay. So that's the scenario. Okay. Okay. So what can we do? Remember, this is the gold standard. Do you know what is the best thing about Monte Carlo simulation? What is the problem with form in terms of computational effort, not in terms of approximation? Efficiency wise, what do you think is the issue with form? That is approximation. I said efficiency wise. Approximation does not result in it. Iterative. Why is iterative a problem? Convergence can be an issue, but that is again. Anything else? Gradient calculation. Gradient calculation is a function of, for 100 random variable, what was the number of calculations we need to do? 101. So it was a function of number of random variable. As the number of random variable increases, your computational cost increases. In this case, do you see k anywhere? So this is the only method available, only, that does not depend on the dimension of the variable. 10 dimension, 1000 dimension, million dimension, it's same. So the problem here is number of samples, but the dimensionality is no longer a problem. It can handle any dimension, and this is the only and only method that can do that. There is no other method that does not depend on the dimensionality of the problem.
So, sir, for the same system, if we do form and this will be much faster. Even though number of samples.
Depends on how many samples. It's a trade-off.
But sir, if the sample is high also, but computation time for doing.
How will it be faster?
Also depends on the number of variables.
Form depends on number of variables and number of iterations, which is equivalent to number of samples. This depends only on number of samples. But form will converge in, you did the homework one, I guess you have done the problem. How many iterations it took? 10? Within 10? So 10 iterations. So how many function evaluation? 10 multiplied by k plus 1. 100 variable. So 10 multiplied by 100. How many simulation? 10,000. 1000. Right? 10 multiplied by 100 is 1000. How many simulation here? Which one is faster? But suppose you have a million variable, then this is into picture. So you cannot give a blanket statement which one is faster. You have to put thing into perspective.
And also, sir, it is also matter the system equation also.
Obviously, but it will not matter of, it will not depend on the system equation, because for computing the gradient you are actually running the actual system equation.
So sir, is it possible that form will take something like more than 100 iterations? Is it possible, sir?
It is possible.
So that's why I'm saying the system is way more complex in that kind of.
Again, when did I say that form will take more than 100 iterations when the system is complex? Did I say that? That is a unconscious decision you are making in your mind. I did not say that. Right? And what do you even mean by complex system? That's a different question. Nonlinear is one, number of variable mode is also one. High number of variable but linear. That's also possible. That's also complex from form point of view, right? But it's a linear system. So depends, what do you mean by complex? Okay, coming back. So we talked about MCS and the major bottleneck is there is only one bottleneck, assuming you can sample, by the way. I'm assuming that, which is the convergence. So can we somehow come up with an alternative version of MCS where this convergence rate can be improved? Can we do that? The answer is yes. Otherwise, I will not be asking that question. Right? So if I am asking the question, I will give an answer as yes. But the real question is how. So there is a scheme known as importance sampling which does that. There are other ways of doing that also, but right now we are talking about importance sampling. Okay. So remember, how were we computing PF? it was integration of the indicator function. I am changing the notation slightly. In the bracket, what was there in indicator function? Gx less than 0. What Gx less than 0 denotes? Failure. So, I will write if. So, it is an indicator function that denotes failure and it is a function of x. You can understand why I am doing that, because I do not want to write a long expression again and again. Multiplied by f x x dx. Can I write it in this form? I f x I divide it by another density. I do not think anyone will have any objection to this. This is the obvious thing that can ever happen. You can always divide and multiply by something as long as that is greater than 0, always. I mean, or less than 0, it will never happen, because then it is not a density, and equal to 0, it should not happen, because then that will go to infinite. So, it should be always be greater than 0. And that condition is kind of obvious, but if that condition holds, then I do not think anyone should have any objection to me writing this in this form, right. Okay. Then, if we can write it in this form. So, okay, let me do one more thing. So, this ratio I will call it Wx. So, can you tell me in terms of expectation what is this equal to? Pf is equal to what? In terms of expectation, tell me. What is Pf equal to in terms of expectation? Should be simple. What is the PDF here? The way I have written it, what is the PDF? H. So, this is I times W. I times W, you can assume it to be a variable a hat. So, integration of a hat multiplied by h dx, that is the expectation of a hat, right. Remember, integration of gx fx dx is equal to expectation of gx, that is the thing we are doing. So, this is expectation with respect to what? H. So, remember, I wrote f today, suddenly changing the notation because of this. Hx I or indicator function f x w x, right. Let me tell you what is the motivation behind doing this. Okay. To understand the motivation behind doing this, you need to understand why the convergence rate is low in case of MCS. Why is the convergence rate low? Mathematics, you know, 1 by root n and all those business, but intuition wise what is happening? Number of samples are very large. Why? Because you are getting very few failure points. If you think about it, what happens? As the PF increases, the number of samples required reduces. You did not what will happen from this expression? Look at the function relation between PF and n. What will happen if PF increases to n? Take coefficient of variation to the right hand side, PF to the left hand side, keep a constant COV, and now tell me what will happen if PF increases? N will decrease, and if PF reduces, N will increase, and that is quite obvious. For a 10 to the minus 15, when I said, you were scared that it will take lots of sample, right? Intuitively we were doing that only, but you were not scared when it was 10 to the minus 2. So, that means when the probability of failure reduces, the number of samples required increases. The reason is that you do not get enough failure point. If the probability is 10 to the minus 15 and if you perform 1 million experiments, you will get 0 failure point. So, your probability of failure will be 0. So, there is a thumb rule. The thumb rule is that you should perform simulation until and unless you get 10 failure points. The moment you get 10 failure points, you can say, okay, now I can calculate probability of failure. That is a thumb rule. A better rule is obviously you do this maths. Okay. So, the issue is that you do not get enough failure points. If you get enough failure points, then you can converge at less number of samples. This is exactly what it is doing. It is now drawing sample from a distribution H, which potentially will allow more failure points. And because of that, you will think that okay, but 10 to the power minus 15. Because of more failure point, I perform 100,000 simulation and I got 5 failure points, right. So, my probability of failure is 5 by 1000. How is my result 10 to the power minus 15? I will repeat. Suppose your actual target probability was 10 to the power minus 15. But because of this scheme, I am saying you are getting more failure points. Let us use the thumb rule. Using the thumb rule, in 1000 simulation, you got 10 failure points. You will stop. Now, your mind will say, but 10 by 1000 is what? 1 by 100. In which world 1 by 100 is equal to 10 to the power minus 15? Right? But that is the mistake you are doing. There is a W sitting there. You will multiply it with a weight factor. So, 1 by 100 multiplied by 10 to the power minus 13, you will get 10 to the power minus 15. So, basically you are allowing more points in the failure zone and then calculating a weighted mean. And because of that weighted mean, that weight factor will ensure you are getting the correct result. That is the intuition behind importance sampling. When importance sampling, okay, importance sampling was there long before, but importance sampling for reliability analysis was proposed in 1998 by S.K. Howe. And for him, this was the intuition, that let us place a density H such that many of the points are in the failure zone, and then let us weight F by H. That weight will take care of the fact that I am not sampling from the actual distribution.
So sir, this H is what it is doing, like it is reducing the PF value in the H and something like
H is not reducing the PF value. H is allowing you more samples in the failure zone.
So that means the PF value in the H will from 10 to the power 15 it will reduce.
That is not that. First of all, what you are saying is increasing, not reducing. 10 to the power minus 15 to 10 to the power minus 2 is increasing. First of all, I understand what you are saying. So, that is not reducing. But to add it, it is not doing anything like that. PF you are not calculating, you will not do 10 by 100, 10 by 1000. That is not the correct way of doing calculating PF. Your PF formula is sitting here. Is it 10 by 15, 10 by 1000? No, it is 10 multiplied by that weight factor divided by 1000. So, 10 multiplied by 10 to the power minus 13 divided by 1000. So, if you are doing 10 by 1000, that means nothing, right?
Basically, it is then reducing the samples, overall samples. It is taking selective samples.
It is not taking selective sample, it is sampling in the failure zone. It is not rejecting any sample. If it was reducing sample, rejecting sample, when you are saying selecting, that means I have a large number of samples, I will select some of those, correct? But then those large number of samples, who is going to give you? It is not doing that. It is just doing less number of samples, but it is sampling from a distribution where more points will be in the failure zone. It is doing nothing else. Now, obviously, you can ask how is it doing it? That I am not answering now. How is it doing it? I am not answering now. But that is the intuition behind it. So, this is the expression to answer your question. This is equal to what? 1 by n summation I equal to 1 to n I f of xi multiplied by w of xi, where now xi is sample from hxx. Okay. This is known as importance sampling. H, the distribution from which you are sampling, is known as importance sampling density. W is known as importance sampling weight. Okay. This is known as importance. Is stands for importance sampling weights. This is known as ISD, which stands for importance sampling density, and the method is known as importance sampling. Okay. Any doubt? So, now if there is no doubt, remember I chose the example very selectively. I chose a distribution H which was such that it was allowing 10 failure points out of 1000, but I can always also choose or have a H which will allow 0 failure point in 10 to the minus 10 to the 20 simulation. So, this is a two-way sword, it can reduce the efficiency also. So, if I was sampling from the original distribution which is fx, let us say in a million sample I was getting 1 failure point, let us assume that. Now, H I can select such that in 1000 I will get 1 failure point, but there can also be a H in which in 1 billion I will get no failure point. The latter obviously is destructive to your cause. The point I am trying to make is that selection of H is very important for getting accurate and efficient result. You should select H properly. The main challenge is that select H that will reduce the variance or and increase the convergence. Okay. Main task is select suitable ISD. Main task is you have to select suitable importance sampling density, without which you will not be able to do anything. Okay. I have what? 5 minutes, right. So, I wanted to find the optimal optimal H, but that will not be possible in 5 minutes. I will need something from variational calculus there. So, rather let us try to see whether it is an unbiased estimator or not. So, do you think it is an unbiased estimator or it is a biased estimator? No guess, you have to explain whatever you think. How will you find out whether it is a biased or unbiased? Take the expectation. Expectation of what? This summation term with respect to what? H. Take that. That expectation will go inside that summation. What is expectation of I f x I w x I? Integration of I x, I f x, w x, h x, dx. What is w x? F x by w x. W and f x by h x. H and h will cancel out. What will be remaining? I f f. What is that? So, expectation of summation of P f, you end up with P f. So, that means it is also a unbiased estimator. I will do it, but I do not need to write it to do it actually. So, expectation of P f hat for importance sampling is equal to 1 by n summation, and now I am doing the expectation integration I f x w x is equal to f x x by h x x multiplied by expectation with x x x dx. This is equal to your P f So, this total thing is equal to your PF, therefore, it is an unbiased estimator. Okay. It is an unbiased estimator. Right? Clear? What is the variance of this? Variance of this estimator? Because variance of the estimator is what we will want to. Variance of the estimator is what we will want to minimize. Because minimizing the variance of the estimator is equivalent to accelerating the convergence. 1 by root n, that was variance, right? So, variance is what we will try to minimize, right? What is the variance of this estimator? One by n summation. If I take variance, 1 by n will become 1 by n square. Variance of Ax is equal to a square variance of x, and then IID. So, variance will go inside the summation. So, 1 by n square summation variance of this estimator, right? This thing, this whole thing, variance with respect to h, by the way, I of xi, if actually, right, multiplied by w of xi, right? Any doubt with this? Is this fine? What I have done is nothing. I have used this formula, variance of A plus B is equal to variance of A plus variance of B, assuming A and B are independent, which they are because xi's are independent, and I have used variance of Ax is equal to A square variance of x. These are the two properties, two obvious properties that I have used. Okay. Any doubt on this one? Is it fine? Now, what is variance equal to in terms of expectation? Summation expectation with respect to h. What will be inside? I square w square, right? I square w square. What is I square equal to? I. 1 square is 1, 0 square is 0. So, I square is equal to I. I f of xi, and w will become w square. Minus expectation of h I f xi w xi whole square. So, expectation square. What is the second term equal to? What is the expectation of that thing? We just derived Pf. So, that second term is equal to Pf square. So, this is equal to 1 by n square summation expectation of h I f xi w square xi minus Pf square, and this is still inside the bracket, right. Now, from here can I somehow find out what should be my h? If I want to find out what should be my h, the best h, what will I do? I will take derivative of this variance with respect to h and equate it to 0 under the constraint that What is H? What is H? It's a PDF. What property? What every function is a PDF? Integration of Hx should be equal to, that is the constant, but H is not a variable, H is a function. So, can you take derivative with respect to function? You have to use variational calculus. So, you have to take the variational derivative, right? We will do it in the next lecture. I am just writing this down. I will start again from the variance derivation, by the way. As usual, I start from last topic, right. So, I will start from variance derivation next time, and we will find out what is the optimal importance density, ISD, and we will see it is useless. After deriving, you will realize that it is useless, you cannot use that. Okay. And then I will give you some practical scheme of how to use importance sampling in practice. So, next lecture we will wrap up this discussion. Okay. I think maybe we can start subset simulation also. Okay. Thank you.